Long short-term memory (LSTM) is an advanced version of recurrent neural networks (RNN). With its unique gating mechanism, it solves the vanishing gradient problem in traditional RNNs and excels at capturing long-term dependencies in sequential data, from speech recognition to stop prediction. Lstm is widely used across various fields. The secret of Lstm lies in its three key components. First is the cell state, the information highway that runs through time, responsible for preserving and transmitting long-term information. Then is the hidden state, the memory snapshot exposed at each time step, used for computing predictions or passing to the next step. Finally are the three gates, which precisely control the forgetting, updating, and outputting of information. Let's examine these three gates in detail. First is the forget gate, which determines which memories should be discarded. Its formula is shown in the diagram. The forget gate outputs a value between 0 and 1 using the sigmoid function, where 0 means completely forget and 1 means fully retain. In a language model, it actively discards irrelevant grammatical structures while focusing on semantics. Here, H and X represent the hidden input and the current input, respectively. The hidden input specifically refers to the hidden state from the previous time step, which is also the output result of each time step and the model's summary of the current moment. The X input is the current input, the raw data the model receives at the current time step. The two vectors are concatenated, multiplied by the forget gate's weight matrix W, and added to the forget gate's bias term, both of which are learned during training. A result inside the parentheses is then passed through the sigmoid activation function, compressing the value to between 0 and 1, yielding what is called the forget probability. The higher the value, the more is retained. Next, we move to the input gate. We again concatenate the hidden input and the input vector, multiply them by the input weight matrix at the bias term, and pass the results through the sigmoid function. The resulting I, ranging from 0 to 1, represents the proportion of new information to retain. The weights and bias here are also learned parameters. I is called the input gate signal because it determines how much new information to keep. Then we multiply the hidden input and input by the other weight matrix, add the bias term, and pass it through TANH, this time compressing the value to between -1 and 1. This gives us a candidate memory value, presenting potential new memory based on H and X. In the third step, we apply the previously obtained forget probability to the cell state from the previous time step, multiplying the retained information proportion by the candidate memory value. Simply put, it means retaining a certain amount of old information while adding a certain amount of new information. The resulting C is the new cell state. To use a vivid analogy, it's like retaining 80% of the subject while adding 20% of a new verb. Finally, we come to the output gate. We multiply H and X by the weight matrix, add the bias term, and pass it through the sigmoid function to get the output proportion O. The larger O is, the more is output. The cell state is passed through TANH and then multiplied by O to obtain H. The hidden state at the current time step, which is also the output result of Lstm. These three gates together from Lstm. In the next section, I will share practical code examples of Lstm to show how it is actually implemented. If you are interested in AI, feel free to follow me. I post daily updates.